Got it? All right. I will I will begin. Dear Father, we thank you for this day. I thank you for the students. Just pray that you'd just bless our work today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. All right. So today, I think you will enjoy both the proofs and the application. So I will start with a theorem, which is this, Theorem 3.17, which states the following. If G and H are finite cyclic groups, then the Cartesian product, the external direct product, G cross H, is cyclic. The product group, anyway, of G and H is cyclic if and only if the order of G and the order of H are relatively prime. So, in other words, the direct product of relatively prime order cyclic groups is itself a cyclic group. And that's an if and only if result also. Yeah. All right, so the proof is two parts. And let's see here. So let's assume that the order of G, well, let me follow my notes. Let me not be an idiot here. Suppose order of G is equal to M, the order of H is equal to N, and the greatest common divisor of M and N is 1. In other words, they're relatively prime. Also, suppose that G is generated by A and H is generated by B. In other words, I'm assuming G and H are both cyclic, one with generator A, one with generator B. All right? Notice that the least common multiple of M and N is equal to what? If we have two relatively prime numbers, what's their least common multiple? Just their product, right? Yeah. So this is Mn. Thus, the order of A comma B, right? As we proved last class, or maybe I didn't prove, but at least I claimed it, right? This is liberty. We name it and claim it, right? Okay. So least common multiple of the order of A and the order of B, but the order of A and B are M and N respective, which of course is Mn. So what do we have? We have an element of order Mn, right? Thus, A comma B is an element of the Cartesian product of G cross H, and the order of the element is equal to the order of the set. What's the order of the Cartesian product of two finite sets, one of order M, one of order N? It's Mn, yeah? So, therefore what? Therefore, G cross H is cyclic, right? Because it has an element that generates the whole group. So thus G cross H is in fact generated by the pair of generators, one from each subgroup. This proof is worth going through because it's not just a proof, it's also a general advice, right? If you want to find a generator for the Cartesian product of two finite cyclic groups of relatively prime order, the generator is obtained by just taking a pair of generators. right? So this is a guide for how to construct the generator in G cross H, not just a proof, right? There's computational wisdom in this proof. Now the other direction, conversely, suppose G cross H is cyclic. All right? And let the order of G be M and the order of H be N, right? And I say define D as the greatest common divisor of M and N. All right? All right, so I say consider x comma y a generator of G cross H, yeah? So what does that mean? I mean, does it exist? Why does a generator of G cross H exist? It's what? It's cyclic, right. So notice we have a couple things for this. X is where and y is where. X is in G and y is where? Right. And what do we know about the x to the order of G? And what about y to the order of H? In other words, x to the m and y to the n. Remember we have, yeah? Has to be the identity, right? Because any group, if we raise the element in a group to the order of the group, we get the identity. This was a corollary to Lagrange's theorem. It was pretty easy to prove, too. So E. Then what? So observe then, and you tell me why this power is a legitimate power to raise. Why can I take the mn over d power? Why does that make sense? Yeah, how do we know that's an integer? That's my question. So it divides both of them individually, right? So that can be reduced to an integer. In fact, two different ways, right? In fact, we know that m over d and also n over d are separately integers, right? So this is x to the mn over d, comma y to the mn over d by the rules of how we do powers in the direct product group. It's the product of the Cartesian product of the powers. And then you just look at this different ways, right? This is on the one hand x to the m to the n over d, but it's also y to the n to the m as in mommy over d. So y to the n as in no is e. So you got yourself an e, and you get your e to the nud to the mud. Anyway, it's e, which is e. So that shows you what? That shows us that mn, right, is equal, well, mn is by assumption the order of x comma y. Why is that? Why do we have this equality? Because remember, x comma y is a generator for the cyclic group G cross H. How big is the cyclic group? How big is the group G cross H? The order of G times the order of H, which is mn. So this equality is given to us because xy is a generator. And we also know that this is less than or equal to mn over d. How do I know that? Because I just proved that if we raise xy to the mn over d power, we get the identity. Right? So that means mn over d is at most what? It has to be a multiple of the order of x comma y, right? So anyway, this directly proves that the order of xy is less than or equal to mn over d. How can we have that? What does that force d to be equal to? And that forces d equals to 1 because we're talking about integers. Therefore, m and n are relatively prime. There you go. So that is the proof of theorem 3.3.17, which is the base of much of our logic in problems that we do in this course, yeah? So corollary to that, which is worth writing down again, is that z, mn, is isomorphic to zm cross zn if and only if m and n are relatively prime. The proof is just to apply the theorem we just proved. All right? Now, I'll probably talk more about the direct product of 3 or more things in the help session today. I'm gonna talk about 3 or more things in the help session today. I'm going to try to focus our lecture on 2 things, okay? Direct products of 2 things, and things about direct products of 2 things. Because that's what I primarily test you on, and and if you understand that, it's straightforward to go to 3. So, I say that, but then I'm about to do a problem. I'm about to write down an example with this. Direct products of who knows how many things. I'm an idiot. So oh well. So just don't listen to me from 30 seconds ago. All right, so example. Find distinct isomorphism classes of finite abelian groups of order, let's see here, let's try to make it interesting. $108. Now 108 is 4 times 27. Oh, wait a minute. Oh man, I can't do math today. That's not good. Is that 4 times 27? I want 4 times 27. What's 4 times 27? Oh, okay, good. All right. Again, I have trouble trusting me from 10 seconds ago. But, all right. Ignoring my self-referential problems of doubt. 3 to the third. I have no Cartesian problems, though. Like, I've never really worried about whether or not I'm here thinking the thought that I'm thinking, whether or not people really exist to hear me, because it's just dumb. Sorry. It's just, I mean, why worry about that? If you're going to worry about that, why are you having conversations with people that don't exist? Much less caring about what they think. Get it. Anyway. So the fundamental theorem of finite abelian groups, fundamental theorem of finitely generated abelian groups, says, the fundamental theorem of finitely generated abelian groups, says that any finitely generated abelian group is isomorphic to a direct product of cyclic groups of prime power order. So it says that, basically it just says this. If you have G, it is isomorphic, such a G, again, finitely generated abelian group. It's isomorphic to Z to the P1, P1 to the K1, Z, P2 to the K2, etc. PS to the KS. This is distracting you. I'm going to get rid of it. All right. It is written in the notes. You could have come up with the abbreviation for it if you like. But the bottom line here is that we can look at. I just wanted to give you an example of how this actually is a helpful theorem, because if we're thinking about groups of order 108, then the way to do that, there's a couple different ways. One way we could have is z to the, 2 squared cross z to the 3 to the third. That's one possibility. But we could also break that up into z2 cross z2 cross z to the 3 to the third. Yeah? Or we could break that up into z2 to the squared cross z3 squared cross z3. Or we could do z2 squared cross z3 cross z3 cross z3. Or we could do z2 cross z2 cross z3 cross z3 cross z3. I think them's your choices. These are the ways that we can break up, we can factor. Like if you look at 2 to the 2 times 3 to the 3, these are the distinct ways you can factor those products of primes as products of prime powers. I mean, this is the distinct number of ways you can multiply these numbers together and get 2 to the 2 times 3 to the 3, right? If you multiply these guys, you get back to those. And there's no other possible way to factor it. Am I right? How many is that? I mean, we found 5 in this case, I guess. That seems wrong. I'm missing something. What am I missing? 3 squared in the... So I need 2, 2, and then what? 2, 2, 3 squared, and then a 3? Okay, that's better. See, because the basic thing here is if I have a group of order 27, the possible ways to do that, we could do Z27, we could do Z3 cross Z9, we could do Z3 cross Z3 cross Z3. These are what I'm looking at is a representative of each possible isomorphism class of finitely generated abelian groups of order 27. These are not isomorphic. Why? It's easy to show that these are not isomorphic because they have elements. I mean, one is cyclic. Is this cyclic? It is not, because 3 and 9 are not relatively prime. So this is not cyclic, which you can easily deduce from other things. Like it has more than the allowed number of elements of particular orders if it was cyclic, yeah? This has many more elements of order 3 than this does. This has even more elements of order 3 than that does. So you can easily see that they have different numbers of elements of different orders if you just start fussing with it. And the same is true for every one of these 6 possibilities. So there's 3 possibilities for the 27. The 2 squared, though, that's a group of order 4. We've already seen that. That's either Z4 or it's Z2 cross Z2. Those are your 2 possible finitely generated abelian groups of order 4 up to isomorphism. Now, are there other finitely generated abelian groups of order 4? Absolutely. They're up to isomorphism, right? You could talk about other things that had the same group structure but were not this, right? Like, for example, U5. Isn't U5 such a thing? Isn't this isomorphic to U5? U5 was what? 1, 2, 3, 4. How do you know that this is Z4? Well, how many numbers are relatively prime to 5? Mod 5. 1, 2, 3, 4, right? So P minus 1. So these are all generators. Oh, they're not all generators. 2, 3, and 4 are all generators, I think. Well, I'm saying this wrong. How to say this more concretely? How about 2? Just look at 2. What's 2 squared? What's 2 cubed? What's 2 to the 4th? 1. So 2 is an element of order 4 in U5. That proves that U5 is up to isomorphism Z4, because it has an element of order 4, right? Does Z2 cross Z2 have an element of order 4? No, it does not. It has 3 elements of order 2, and it has the identity. All right? So my point to you is just that when we think about a group of order 108, basically there's 2 things going on. There's splitting up the 27 piece of it, which can go any of these flavor options, and then you split up the part of it that's got, you know, the order 4, and it either splits to a Z4 or a Z2 cross Z2. But then you can do either option, so you multiply. That gives you 3 times 2, which is 6 possible non-isomorph, 6 distinct isomorphism classes of groups of order 108. Now, if I drop the abelian, and if we think about possibly non-abelian groups of order 108, then I have no earthly idea how many of them there are, or if there are any at all, right off the top of my head, because I am not a group theorist. I am merely teaching you group theory. Yes. All right. Anyway, I hope that discussion is helpful to you, and it brings the fundamental theorem of finitely generated abelian groups a little bit more to life. Really, to apply the fundamental theorem of finitely generated abelian groups, that is most powerfully married to this corollary, because the corollary allows you to do things like write this more nicely, which is, this is just Z108, right? Because these are relatively prime, right? And there's other simplifications you could make, right? Like this. Now, excuse me, Z equals, don't let me get away with that. There's not equality there. It's isomorphism. And this is isomorphic to Z2 cross what? You can combine these. 2 times 54 is what? Well, 2 times 27, rather. 54, right? This would be isomorphic to, well, there's 2 different things you could say it's isomorphic to, right? You could say this is isomorphic to, these are relatively prime, right? What's 4 times 9? So Z36 cross Z3. But that's also isomorphic too, because I could have gone and I could have combined, oh, wait a minute. Yeah, I could. I could have combined this and that. That would have been what? 4 times 3 is 12. And 9. These are, I'm just using this corollary to simplify these. And here, I mean, you got different ways you could simplify it. I mean, we could do Z12 cross Z3 cross Z3. Okay, actually, that's it. That's it. But this one maybe is more exciting. We could do Z2 cross Z6 cross Z3 cross Z3. Oh my goodness. I've dropped my isomorphism. That is very bad. I'm not joking. Z6 cross Z6. You'll find out in the next test. So Z3 cross. So now I'm combining these 2. You're like, you can just move them around like that willy-nilly? Yeah, you can. Because there is obvious isomorphisms between, like, is G cross H isomorphic to H cross G? And if so, what's the isomorphism? YX, right? And you can prove that that's an isomorphism. Because these are just different notations for the same stupid group. It's just a question of labeling. Which is the first, which is the second, which is the third component. Yeah? Anyway, I'm going to stop there. I just wanted to show you that there's lots of, like, if you were going to give this to a class and wanted to grade it, it would be in your vested interest to force them to write, like, something. You give them guidance that somehow forces them to write one of these, like, uniquely, right? Otherwise, the grading, you got to look for either this or that or that. And they're going to make mistakes, so they're going to have the same answer twice, you know? So, just saying. Wait a minute, you guys are not teaching this, so why am I telling you that about? All right, enough. Next up, what is, so we're now into lecture 14, very exciting. And so proposition, a couple propositions that you guys are going to like. If p is prime, then the order of the group of units is equal to p minus 1. Hence, phi of a prime, the Euler phi function, is equal to p minus 1. Also, another proposition, if p is prime, then the order of the units of p to the power k are equal to p to the k minus p to the k minus 1. Hence, phi of p to the k is equal to p to the k minus p to the k minus 1. Both of these propositions are simply proved by looking at the numbers that go from 1 to p, or 1 to pk, and just eliminating the ones which are multiples of p, or multiples of p to the k. And, well, not multiples of p to the k, but let's see here. It's not a multiple. You got to look for things that have a common divisor with p to the power k, right? So if you think about that, that's going to be your what? Multiples of p, right? For example, it's easier to think about if we think about a specific one for this one. If we think about 5 squared, right? If you think about, U25, what are you looking at? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Why did I do this? 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Obviously, I need to put some divisions in there, otherwise you can't read it. That makes it worse or better, I don't know. Which one of these, which of these guys are not relatively prime to 25? 5, 10, exactly. The 5, 10, the 15, the 20, the 25. So how many is that? That is 5 to the 1. And so the net number is 5 to the 2, right? So 5 to the 2 minus 5 to 1 is equal to the order of U25. Now, of course, that is not a proof, because I've just done it for p equals to 5, but the argument for arbitrary prime to the power k is actually the same. And I've tried to prove that in previous years. You can go back and look at how that went. Let us go on. You got to know your battles. I know that's one I don't fight in here. So our next result is Theorem 3.4.3. And this is, you've been waiting for this one. This one's great. If the greatest common divisor of, let's say, R and S is 1, then the group of units, oh, I meant S and T. I'm sorry, I can't read my own writing. S and T. Then the units of order UST, ist, is isomorphic to us cross ut. There we go. So in fact, if we have, looking at the group of units of order 21, that's isomorphic to U3 cross U7. If we're looking at the group of units of, say, 50, that's the group of units of 2 cross the group of units of 25. et cetera, et cetera. And of course, we can always take n and factor it, right? So this is amazing. This pretty much gives us the ability to figure out what groups of units look like up to isomorphism with just a few more lemmas. There's like a few little results we need to really make good on that computationally, but this is the central fact. And I'll just tell you, I'll sketch the proof for you since I have blathered on about uninteresting things too long. But the proof is really just this. You take the ST equivalence class of X and you map that to X sub S, comma X sub T. And this actually defines the isomorphism. This defines the isomorphism from UST to US cross UT. That's it. The proof that that is an isomorphism has many stages. First of all, you need to show the map is well defined, right? Because I'm defining in terms of representatives of cosets. There's a question there that needs to be answered. Details are in the notes. Then, of course, we have to prove the homomorphism property. That's relatively easy. Finally, we have to prove it's a bijection. Because these are two sets, because this is these are both finite sets, right? It suffices to prove that it's injective, right? Is that right? I think I also need to know that they're the same size, don't I? To do that? Well, anyway, it's interesting, though, to show that it is injective. There may be a gap in my proof. But anyway, to show injective, it boils down to to show it's injective, right? You want to show that the kernel of psi is equal to the identity, yeah? And what does that mean? That means that xs is equal to 1, and also x sub t is equal to 1. What's that mean? That means you're solving, you're trying to solve x congruent to 1, and you're trying to solve x congruent to 1 mod s, mod t, right? And why does a solution exist? What theorem gives us the existence of an x? Yeah, the Chinese remainder theorem says that we can solve these because we're talking about relatively prime moduli, S and T. So actually in this section, I have not just a proof of the Chinese remainder theorem, but the proof of the Chinese remainder theorem for not just two, but for finitely many relatively prime congruences. I'll project the proof here in just a second. It's not bad. So once we have this theorem, which admittedly I'm just sketching the proof of for you guys today, a straightforward corollary is that the Euler phi function of ST is what? Or Euler phi of S times Euler phi of T, yeah? All right. I'm going to start projecting because I want to make sure that I don't go too fast through the encryption. So in the interest of not just rushing through the encryption at the end, I'm going to eventually find where I put my, oh, there. It's like, where's my laptop? It's important that you work through the proof of that theorem. That makes like a very decent test 2 question. There's a lot in that proof, which are things that I want all of my abstract algebra students to know. Like verifying that a function actually is a function. You guys had a lot of problems with that on test 1, right? Yeah. So about half of you still have not settled in your mind what a function is. Like, you know, but you don't know. I'm not in the school of thought like you're completely unaware, you're just completely clueless. I don't believe that for a second. I think you have a fuzzy notion of it that's just not quite making it to the test, right? Or just the details of the example I asked about, you can't figure out for whatever reason. You got some mental block about the particular example I asked you to show was a function, or not a function actually. But the proof of this is a good exercise into showing, because to show that this actually is a function is to show that this is single valued, And there's a question to resolve there because, this is a representative, that's a representative, that's a representative. It's not guaranteed that this is a single output. There's actually something to show there, and it's actually kind of interesting to check there as opposed to my test question about Z3 and Z6. That's kind of boring. This is more interesting. So I would encourage you, work through this proof for yourself. I shut up about that. So, these are the details that I was just talking about. They're not bad. I'm going to use our time for other things today, okay? So I will discuss, words. So this is the Chinese remainder theorem I was talking about. If we have relatively prime moduli as M1 through MR, and we're trying to solve this system of congruences with these relatively prime moduli, then the Chinese remainder theorem says that in fact there exists a solution, and it is unique modulo the product of the moduli, which we'll call big M. And the proof, it's really very nice, not that hard. You just define M sub k to be the product divided by M sub k. If you look at that, it's got every one of the moduli except for M sub k. Right? Which means that the M sub k is 0 mod anything in the list of M1 through MR except the kth one. So when I look at this, if I look at it like mod, mod M sub, and any modulus except for like mod 2 through mod R, this one will be 0. The only thing that this is non-zero is for mod 1. If I look at mod 1, all of this dies by construction. It's very nice. So again, long story short, X is congruent to AI, MI, YI, which is by construction congruent to AI. So here I've used the fact that the M sub k and the little m sub k is relatively prime. That means we can use Bezau's theorem to select this Y, which then I use math magic to construct the solution like so. But this proof, the reason I'm even spending class time to talk about it, it actually shows you a straightforward algorithm to solve that many congruences by just constructing these M sub k's. There are other ways to do it, I'm sure. And you're like, shouldn't you have shown us this before you put that on the first homework? Yeah, probably you got me. But I didn't test on it, did I? I just regretted it when I was like, this homework was supposed to be moved till later. So sorry about that. Now, most of you didn't notice it because you've had Chinese remainder theorem and like number theory or something else. But for those of you who didn't, I'm sure that was kind of a shock. I'm sorry about that. My apologies. So, if you had asked me about that, I would have told you, yeah, I'm not really going to test on that. But nobody asked me. So, oh well. All right. Here's an example. Let me go on. So, again, I'm going to talk more about this in the help session, but we can continue to more than two things. All right? And because we continue to more than two things, the Euler phi function, as long as we're looking at the product of relatively prime things, it's multiplicative on such things like this. And then, so long story short, because any natural number can be factored as the product of primes, distinct primes to particular powers, right? Fundamental theorem of arithmetic. When you fit that into the theorem that we just, corollary up here, and the theorem that we just discovered, then that says the group of units n is isomorphic to a direct product of prime of the units of prime power order, like so. Which is pretty nice. And then these can also be reformulated into Zn cross Zm for appropriate n and m. I probably shouldn't use n here, but for appropriate Z mod whatever, Z cross whatever. I mean, in particular, here's the tools. You know that U2 is the 0. It's the trivial group. U4 is Z2. U2 to the n, it turns out, is Z2 cross Z to the 2 to the n minus 2. This I don't prove. I mean, that's probably a dastardly homework problem right there. I'm not sure I've seen the proof of that. I know that this is apparently due to Gauss in the early 19th century. And then if we have a odd prime, so this is just for 2, but for odd primes, the unit group of units, p to the n, for an odd prime, it's just a cyclic group, actually. So, for example, U20, or rather U25, U5 squared, right, is going to be isomorphic to what? How many things are in U25? We just figured out 20. I'm telling you here it's cyclic. So U25 is isomorphic to Z20 is what I'm saying. And that is very powerful because that means that you can take groups of units and you can figure out what they are up to isomorphism. You can find out how they're isomorphic to particular copies of modular integers, like this. Like 200 is 5 squared times 2 cubed. So we use the theorem, break it up, then use the fun fact here to break that down into Z25 minus 5. And we've already seen this. U8 is Z2 cross Z2. This we've actually worked out, right? That's the Klein 4 group for U8. 405 breaks up like that. 195 breaks up like that. Now, why would you care about this? We had a problem, a homework problem that said the automorphisms of Zn are isomorphic to what? Automorphisms of Zn are isomorphic to the group of units, mod n, right? Aut Zn is isomorphic to Un. So now we have the technology to figure out the order of automorphisms because we can figure out what the automorphisms look like in terms of direct products of these. Let me show you what I mean. So here's a question. How many automorphisms of Z100 have order k? All right. Well, since aut Z100 is isomorphic to U100, we can trade the question for the related question of how many elements of order k are there in U100. But that's actually very manageable because we can trade U100 for U4 cross U25, which is Z2 cross Z20. And then the question is how many elements of order 4 are there, of order k are there in here, you know? Well, and take a specific example. We can look at k equals to 4. To get an element of order 4 here, you either can take the identity cross an element of order 4, or you can take an element of order 2 cross an element of order 4, right? So it's twice the number of elements of order 4 in here. How many elements of order 4 are there in Z20? 5 is one of them. Also 15, right? 5 and 15 are the elements of order 4 in Z20. And so in total, 2 times 2 is 4, because I can either do the 5 or the 15 paired with the 0 or the 1 over here. Oh, here they are explicitly. These are the explicit elements of order 4 in Z2 cross Z20. But because isomorphism preserves order of elements, we have just proved that the number of automorphisms, that is bijections from Zn or Z100 to Z100, which when composed with themselves 4 times give you back the identity, but not before that, is 4. There are 4 automorphisms of Z100 of order 4. This is actually not a difficult problem with this stuff in mind. Without this stuff in mind, whoa. Whoa. Now, if you'd like to see an even more dastardly example, you can look at Galilean's page 156. That finally brings me to my last, as I was selling for you guys, encryption. So we can prove Fermat's little theorem with what we have Fermat's little theorem says that if we have p as a prime, then a to the p minus 1 is equal to 1 mod p. Now, some of you would fuss, I should put congruent to 1 mod p. You got me. So the proof is given right here. And it's straightforward. I'll let you look at that. And we also have Euler's theorem, which says that if we have x is in the group of units mod k, then x to the Euler phi function of k is 1. This is not surprising. This is just that any group element to the order of the group is equal to 1. The order of the unit group of units is phi of k. So this is kind of like duh. Euler's theorem is a kind of a duh theorem for us, given the other things we have. But of course, you work kind of hard to prove these things. If you see the proof of these in number theory, it would look nothing like this, right? You would prove these things a rather different way, probably by direct combat with congruences and such, right? So this brings me to the story of encryption. Encryption is basically a sneaky one-way mathematical game based on modular arithmetic. And the idea is this. Well, let me just go through the algorithm. The basic idea of encryption is we want to be able to hide something in plain sight. And not just that, not only are we hiding it in plain sight, we tell everyone how to hide their own thing in plain sight. And yet somehow it can't be seen by anybody but you. That's weird, right? It's really weird. I mean, classically, when you think about hidden messages and things, if anyone was to discover the key, whatever it takes to unlock the encryption, it would be over for you, right? Like your encryption would be broke. I think, how did we do it in World War II? We had, there's movies about this, right? I think we used the Navajo Indians because that was a native tribal language, and how on earth would the Japanese ever figure that out, right? That's a pretty good encryption. It's just bizarre, really. And but on the other hand, I think we actually got one of the Germans' coding machines, right? And so we were able to understand German messages. So there's value in being able to break encryption, right? Fortunately, the Germans hadn't discovered this, because otherwise it would have been bad. Although this is really made possible by computers. So let's go through it. Part 1, you choose a pair of large prime numbers p1 and p2, and you define n as p1, p2. This is typically huge. You calculate the product of the primes, and you choose an encryption exponent such that the greatest common divisor of e with the Euler phi function of n is 1. All right? Step 3, you publish the encryption exponent in n, which is the product of the primes, all right, so that anyone can send you an encrypted message subject to the commonly held convention. For example, you might use the alphabet code, right? You can take any string of letters, right, and you can parse them into so many and come up with numbers that correspond to that. I mean, that's up to you guys, right? Or whoever you are coding. I'm sure there are common conventions here. I mean, I like the alphabet code, 0 to 26, take 4 letters at a time, something like that. Next step. So you come up with an integer m, which represents a message, is the simplest thing to think about, all right? So your friend takes n and e that you publish and runs their message through the map f of m equals to m to the e. That will scramble the message m to the encrypted message f of m. They communicate f of m to you without even hiding it, in plain sight. Anyone could intercept f of m mid-transit, it doesn't even matter. Even if the interceptor knows your n and your e, it doesn't matter. They don't know p1 and p2. They just know the product of p1 and p2. Since you know p1 and p2, you can calculate the Euler phi function of n is this. And you have that e times d equals to 1. I mean, there's an inverse of the encryption exponent, right? And so you have m to the e to the d is this, which is that, which is that. In other words, you have an inverse function to the encryption function. You can undo it because you know the primes which formed your n. So here, let me run through this example with you. Hopefully this makes what I just ran through make more sense. So we have, say, 13 and 17. That would give us 221. This is a toy example. In actual encryption, the primes which are used for encryption are so stupidly huge that after you multiply them, you can't undo it. Like, the numbers are so big that the process of finding the prime factorization of them is just not feasible. That's what decrypting means, is that's somehow like finding prime factorization or something like that. So Euler phi function is this. I'm going to choose the encryption exponent as 37 because it's relatively prime to 192, which is the order of the group of units mod 221. My public key then is I'm going to use 221 and an encryption exponent of 37. My friend chooses the message 10. Then you have to calculate m to the 37 mod 221. So that's 10 to the 37 mod 221. Now that seems kind of hard, but you use a trick. You look at 37, you break it up into sums of powers of 2. These then makes the exponentiation, use this binary exponentiation trick, makes it easier. So you do, well, like this. Anyway, you can look at how this is going on. That's just a trick for fast exponentiation. Bottom line is, after some calculation, we get the encrypted message is 23. Started with 10, we got to 23. Now my private decryption key requires me to calculate the multiplicative inverse of 37 mod 220 mod 190 modulo 192. So I go through that. This is the standard, Euclidean algorithm backward substitution stuff. After a little bit, I figure out that the inverse of 37 is 109. That means that if I take the encrypted message and raise it to the 109 power, mod 221, then I should get back the unencrypted message. So I calculate that here, 23 to the 109 power is 10. Yay, we've unencrypted the message. That's how it goes. So as you can see, my friend sent me the coded message 23, and I was able to decipher it as the hidden message of 10, just like that. Now the thing, it's hard to appreciate this from the toy example, but you got to understand, when we use n is the product of primes that are very, very large, we're talking about n having hundreds of digits. How do you find the prime factorization of something with hundreds of digits? That's what is keeping your email secure right now, is the fact that no one can do this. Now, the minute somebody figures out a quantum computer and or how to program it to effectively break encryption, well, then you should worry about, saying stuff about the government over your emails. Or maybe you should already worry. Maybe they've already broke it. I don't know. Ask Dr. Smith. He knows more about this sort of thing. Now, just finally, a cautionary tale, and then I will let you go for the week. I mean, I know your weekend's about to start. I'm sorry to keep you from it. But when I first did this in number theory, I chose an encryption exponent of 49. I said, here's my message. I gave them whatever message it was, and I said, you guys encrypt it, and I'll come back. I left the room for a couple minutes. I could come back, you give me the encrypted message, and I'll try to unencrypt it. And I got back, and they gave me back the same number again. I was like, did you guys do anything? Like, yeah, we did. It just came back to 10 again. I was like, what? So I chose 49, which is very unfortunate because that's actually an example of what's called a group exponent. Well, not quite. The group exponent for U221 is actually 48. So anything in U221 raised to the 48 power is the identity, which means if you use 49, the anything to the 49th power is just itself again. So I chose very poorly. So it's actually not enough to choose a group. You must choose an encryption exponent, which is relatively prime to phi of n. Yes, that's true. But you should also choose one that's not close to the group exponent, because that will also be bad. There are, of course, many more nuances to actual encryption, which I will not show you. In fact, I think we have a whole course in it, right? So go take the course. That's a CS class. Well, they're okay. They've got science. It's computer science, right? No? I shut up. Have a good weekend, you guys.